In the ever-evolving realm of artificial intelligence, TensorFlow stands tall as a beacon of innovation and progress, illuminating the path forward for developers and researchers alike. Developed by the brilliant minds at Google Brain, TensorFlow is an open-source machine learning library that empowers developers and researchers to build and deploy intelligent systems with unprecedented ease and efficiency. Its versatility, scalability, and extensive community support have made it a cornerstone of countless applications, from image recognition to natural language processing and beyond. TensorFlow's journey began in 2011 as Dist Belief, an internal Google project aimed at building large-scale distributed neural networks, pushing the boundaries of what was possible in machine learning. As the project matured and gained traction, Google recognized its potential to revolutionize the field of machine learning, leading to its evolution into the TensorFlow we know today. In 2015, TensorFlow was released to the public, ushering in a new era of accessibility and collaboration in AI, making advanced machine learning tools available to everyone. At its core, TensorFlow provides a robust framework for defining and executing computations involving tensors, which are multidimensional arrays of data, essential for complex machine learning models. These computations are represented as data flow graphs, where nodes represent mathematical operations and edges represent the flow of data between them, enabling sophisticated data manipulation. This graph-based approach allows for efficient parallel processing and optimization, making TensorFlow suitable for handling massive datasets and complex models, ensuring high performance and scalability. TensorFlow's impact on the world of technology has been profound, influencing a wide range of fields and applications. Its intuitive API, coupled with its extensive documentation and vibrant community, has significantly lowered the barrier to entry for aspiring machine learning practitioners, fostering a new generation of AI innovators. From self-driving cars to personalized medicine, TensorFlow is driving innovation across industries, shaping the future of how we live, work, and interact with the world around us, making the impossible possible. TensorFlow's remarkable success can be attributed to its rich set of features that cater to the diverse needs of the machine learning community. Its flexibility allows researchers to experiment with novel architectures and algorithms, while its scalability enables engineers to deploy models on a wide range of hardware, from mobile devices to distributed clusters. One of TensorFlow's key strengths lies in its extensive language support. While Python remains the most popular language for TensorFlow development, the library also offers APIs for C++, Java, Go, and Swift, allowing developers to leverage their existing skills and code bases. This multilingual approach fosters collaboration and widens the pool of talent contributing to the TensorFlow ecosystem. TensorFlow's ecosystem extends far beyond the core library itself. A plethora of tools and libraries have emerged to streamline various aspects of the machine learning workflow, from data pre-processing and model training to deployment and monitoring. TensorFlow Serving, for instance, simplifies the deployment of trained models to production environments, while TensorFlow Lite enables the execution of models on resource-constrained devices. Behind TensorFlow's technical prowess lies a vibrant and supportive community of developers, researchers, and enthusiasts. Online forums, tutorials, and documentation provide a wealth of resources for both beginners and experts alike. This collaborative spirit ensures that TensorFlow remains at the forefront of innovation, with new features, improvements, and use cases constantly emerging from the community. At the heart of TensorFlow's architecture lies the concept of data flow graphs. These graphs are fundamental to how TensorFlow operates and processes data. These graphs provide a visual representation of the computations involved in a machine learning model, making the entire process more transparent and easier to follow. This visualization is crucial for understanding, debugging, and optimizing complex workflows, which can often be a challenging task in machine learning projects. In essence, a data flow graph is a directed graph where nodes represent operations and edges represent the flow of data or tensors between them. This structure helps in organizing and managing the computational tasks efficiently. Each node in a TensorFlow graph represents a mathematical operation such as addition, multiplication, or matrix multiplication. These operations form the building blocks of any machine learning model. These operations can be as simple or as complex as needed to express the desired computation. The flexibility of TensorFlow allows for a wide range of operations to be performed. For instance, a node could represent a single neuron in a neural network, or it could encapsulate an entire convolutional layer. This versatility is one of TensorFlow's strengths. Edges in a data flow graph represent the flow of data between nodes. This flow is what drives the computations forward. Each edge carries a tensor, which is a multidimensional array of data. Tensors are the primary data structure used in TensorFlow. Tensors can be thought of as the lifeblood of a TensorFlow graph, carrying information from one operation to the next. Without tensors, the graph would be unable to function. The shape and data type of a tensor are determined by the operation that produces it and the operation that consumes it. This ensures that data flows correctly through the graph. Data flow graphs offer several advantages for machine learning. They provide a structured way to manage and visualize computations. First, they provide a clear and concise way to represent complex computations. This clarity is essential for both development and debugging. Second, they enable parallel processing by allowing independent operations to be executed simultaneously on different devices. This parallelism can significantly speed up computations. Third, they facilitate optimization by allowing TensorFlow to analyze the graph and identify opportunities for efficient memory allocation and execution. This optimization can lead to better performance and resource utilization. Section 4. Nodes and Edges. The essence of TensorFlow's architecture. To fully grasp the power of TensorFlow's data flow graphs, it's essential to delve deeper into the roles of nodes and edges. These components are fundamental to understanding how TensorFlow operates under the hood. Nodes are the building blocks of computations, while edges dictate the flow of data between these operations. Think of nodes as individual tasks or operations that need to be performed. Together, they form a symphony of mathematical transformations that bring machine learning models to life. This orchestration is what allows TensorFlow to handle complex computations efficiently. Each node in a TensorFlow graph represents a specific operation, ranging from basic arithmetic to complex matrix manipulations. These operations are the core of any machine learning model. These operations can be as granular or as high level as needed to express the desired computation. This flexibility is one of TensorFlow's greatest strengths. For instance, a node could represent a simple addition of two numbers, or it could encapsulate an entire recurrent neural network layer. This versatility allows for a wide range of applications. Edges, on the other hand, act as the conduits through which data flows between nodes. They ensure that the output of one operation becomes the input for the next. Each edge carries a tensor, which is a multidimensional array of data. Tensors are the primary data structures used in TensorFlow. These tensors can be thought of as the lifeblood of a TensorFlow graph, carrying information from one operation to the next. Without tensors, the data flow would come to a halt. The shape and data type of a tensor are determined by the operation that produces it and the operation that consumes it. This ensures that data is correctly formatted and processed. The interplay between nodes and edges is what gives TensorFlow its remarkable flexibility and expressiveness. This dynamic interaction allows for the creation of highly customized computational graphs. By combining different types of nodes and connecting them with edges in various configurations, developers can create a vast array of computational graphs, representing everything from simple linear models to complex deep neural networks. This capability is what makes TensorFlow so powerful and versatile. Understanding the roles of nodes and edges is crucial for debugging and optimizing TensorFlow models. A deep understanding of these components can significantly improve model performance. By visualizing the graph and inspecting the values of tensors flowing through it, developers can identify bottlenecks, inefficiencies, and potential errors in their code. This process is essential for refining and perfecting machine learning models. Section 5. Sessions and Execution. Breathing life into TensorFlow models. While data flow graphs provide a blueprint for computation, they remain static entities until executed within a TensorFlow session. A session acts as an intermediary between the graph definition and the computational resources available, allocating memory, initializing variables, and coordinating the execution of operations. Creating a TensorFlow session is akin to firing up the engine of a car. It's the crucial step that brings the static graph definition to life, allowing data to flow through the edges and operations to be executed on the specified devices. Without a session, the graph remains a mere blueprint, incapable of performing any actual computation. Once a session is established, operations can be executed by calling the method on the session object, passing in the desired output tensors as arguments. This triggers a chain reaction within the graph, with TensorFlow traversing the edges in reverse topological order, executing the necessary operations along the way to compute the requested outputs. During execution, TensorFlow optimizes the computation by analyzing the graph and identifying opportunities for parallel processing, memory reuse, and other performance enhancements. This ensures that models run as efficiently as possible, even on resource-constrained devices. Understanding the lifecycle of a TensorFlow session is crucial for debugging and performance tuning. By carefully managing session resources, developers can prevent memory leaks and ensure that computations are executed in a timely and efficient manner.